Alright, let's talk about something truly epic: building a rocket. When you see one of those magnificent machines blasting off into space, it's easy to just be amazed by the fire and the noise. But have you ever stopped to think about what it takes to actually build one from scratch? It's not magic, it's one of the most incredible feats of engineering and manufacturing on the planet. Walking into a rocket factory is like stepping into the world's most advanced workshop, a place where science fiction becomes hardware. It's a cathedral of creation, where raw metal and wires are transformed into a vehicle that can touch the stars. It's a place I could get lost in for weeks. Think of a rocket as the ultimate exploration vehicle. For all of human history, we've been bound to this one planet. Rockets are our ticket to ride, our way of sending people and incredible scientific instruments beyond the sky. They carry satellites that give us GPS and weather forecasts. They send probes to distant planets to unlock the secrets of the universe. And of course, they carry astronauts to live and work in space. Every single one of those missions starts right here, on the factory floor. The dream of space travel is built piece by piece with rivets, welds, and a whole lot of brainpower. It's the ultimate build, and I'm so here for it. Imagine the scene with me. You walk through a massive door and the sheer scale of the place hits you. The ceilings are stories high, big enough to house a skyscraper on its side. The air hums with the sound of machinery, the hiss of welders, and the focused chatter of engineers and technicians. All around you are giant, gleaming cylinders of metal in various states of completion. These are the fuel tanks, the engine housings, the very bones of a future spacecraft. You can feel the energy in the room, a mix of intense concentration and a shared sense of purpose. Everyone here knows they are part of something much, much bigger than themselves. This journey from a pile of parts to a fully functional launch vehicle is the story I want to tell you. We're going to peel back the curtain and look at the secrets of the factory floor. We'll explore the exotic materials, see how the powerful engines are born, and witness the painstaking process of putting it all together. It's a tale of precision, of incredible problem solving, and of a relentless pursuit of perfection. Because when you're building something that will travel thousands of miles per hour and brave the vacuum of space, there is absolutely no room for error. So, put on your safety glasses and let's get building. This is where the magic really happens. So, what do you use to build a machine that has to be both incredibly strong and surprisingly lightweight? You can't just run down to the local hardware store. The materials used in rocketry are some of the most advanced on Earth, chosen for very specific and demanding jobs. The main ingredients are special metal alloys. Think of alloys as metal recipes, where engineers mix different elements to get the perfect properties. A huge player here is aluminum, but it's not the same stuff that's in your soda cans. It's often mixed with lithium to create an aluminum-lithium alloy that is ridiculously strong, but also much lighter than standard aluminum. Every pound you save on the rocket's structure is another pound you can use for fuel or payload. But it's not just about the metal skin. Modern rockets are increasingly built with something called composite materials. The most famous of these is carbon fiber. If you've ever seen the distinctive black weave pattern on a high-performance race car or a fancy bicycle, that's it. Carbon fiber is made of tiny strands of carbon, thinner than a human hair, woven together and set in a plastic resin. The result is a material that is stiffer and stronger than steel, but at a fraction of the weight. It's perfect for making parts like the payload fairing, the pointy nose cone at the top of the rocket that protects the satellite during launch. It needs to be strong but light enough to be jettisoned away once the rocket reaches space. Then you have the really exotic stuff, the materials needed for the fiery heart of the rocket, the engine. The engine's combustion chamber and nozzle have to withstand unbelievable temperatures. We're talking thousands of degrees, hotter than a volcano. For this, engineers turn to super alloys. These are often based on nickel or cobalt and are designed to keep their strength even when they are glowing red hot. Some parts of the nozzle are even made from materials like carbon-carbon composite, which is so tough it was used on the nose cone of the space shuttle to survive the intense heat of re-entry into Earth's atmosphere. It's all about using the right tool, or in this case, the right material, for the job. Finally, you have all the other bits and pieces that make a rocket work. Miles and miles of wiring for the electronics, specialized glass for camera lenses and sensors, and high-strength steel for bolts and fasteners that hold everything together under immense stress. Even the paint is special, designed to protect the rocket from the elements and manage heat. It's a carefully curated shopping list where every single item is chosen after years of research and testing. The materials themselves are a masterpiece of science before they're even shaped into a single part. It's a testament to how far we've come in our ability to create and manipulate the very stuff our world is made of. Now that we have our materials, it's time to start making parts. The main body of the rocket, which is mostly made up of huge tanks for fuel and oxidizer, starts as massive, flat sheets of that special aluminum-lithium alloy. These sheets are so big you could lie down on them. The first step is to curve them into giant rings. This is done using enormous, powerful rollers that carefully bend the metal into a perfect circle without cracking or weakening it. It's a process that requires immense force but also incredible precision. Each ring has to be exactly the right diameter, down to a fraction of an inch. Once you have a stack of these metal rings, you have to join them together to form the long, cylindrical tank walls. This is where one of the coolest tools in the factory comes in, the friction stir welder. Instead of melting the metal with a torch like in traditional welding, this machine uses a spinning high-tech pin. The pin is pushed into the seam between two pieces of metal and moves along it. The friction it creates heats the metal up just enough to make it soft and plastic-like, and the tool then stirs the two edges together into one solid piece. This creates a weld that is incredibly strong, even stronger than the original metal around it, and free of the tiny defects that can form in a normal weld. This process is repeated over and over, joining ring after ring until you have a cylinder that can be over 100 feet long. But a tank needs a top and a bottom. These are the dome-shaped caps you see at either end of the stage. They are made from pie-slice-shaped pieces of metal called gores, which are welded together in a similar way. The dome shape is critical because it's naturally very strong and can handle the immense pressure of the cryogenic liquid fuels inside without needing heavy internal bracing. Every weld is checked and double-checked with X-rays and ultrasonic scanners to make sure it's absolutely perfect. While the tanks are being built in one part of the factory, other teams are working on the other structural elements. This includes the inner stage, the ring that connects two different stages of the rocket, and the engine thrust structure. The thrust structure is like a metal skeleton at the bottom of the rocket that the engines mount to. It has to transfer all the incredible power of the engines to the rest of the rocket frame without buckling or breaking. It's a complex web of beams and struts, all precisely machined and bolted together. Slowly but surely, the scattered pieces of metal are starting to look like the skeleton of a giant. A rocket body is just a fancy can without two things: the brawn to push it, and the brains to guide it. Let's start with the brawn, the engines. Building a rocket engine is one of the most complex manufacturing challenges there is. These are not like your car's engine, they are controlled explosions happening thousands of times a second. The heart of the engine is the turbo pump. This is a spinning turbine, powered by a small gas generator that sucks in fuel and oxidizer and forces them into the combustion chamber at ridiculously high pressures. The blades of the turbine spin faster than a dentist's drill, and have to be machined with mind-boggling precision from single crystals of metal to survive the stress. The main combustion chamber and the iconic bell-shaped nozzle are also marvels of engineering. As we talked about, they have to handle insane temperatures. To keep them from melting, they are actually built with a kind of regenerative cooling system. The nozzle is made of hundreds of thin, hollow tubes brazed together to form the bell shape. Before the super-cold liquid fuel goes into the combustion chamber to be burned, it's first pumped through these tiny tubes in the nozzle wall. This does two things. The cold fuel cools the nozzle, keeping it from vaporizing, and at the same time the hot nozzle wall preheats the fuel, making it burn more efficiently. It's an incredibly elegant solution to a very hot problem. Meanwhile, in a completely different part of the factory, a clean room, technicians are building the rocket's brain. This is the avionics system, which stands for aviation electronics. This is where you find the flight computer, the navigation systems, and all the sensors that tell the rocket where it is and where it's going. Technicians in full-body clean suits looking like they're from a sci-fi movie, carefully solder tiny components onto circuit boards. Even a single speck of dust could cause a short circuit, so the air is filtered to be cleaner than an operating room. Every connection is inspected under a microscope. It's slow, meticulous work that requires a surgeon's steady hand. These two worlds, the heavy metal of the engine shop and the delicate electronics of the clean room, have to come together perfectly. The flight computer is the conductor of the orchestra. It takes in data from gyroscopes and GPS, calculates the rocket's position thousands of times per second, and then sends precise commands to the engines. It tells the engines when to fire, how much to throttle up or down, and how to swivel, a process called gimbaling, to steer the rocket on its exact path to orbit. Without these brains, the powerful engines would just be an uncontrolled bomb. One is useless without the other. Okay, so the factory floor is now filled with these incredible high-tech pieces. We have our giant fuel tanks, our powerful engines, and our super smart avionics boxes. Now comes the part that honestly feels a lot like building the world's biggest, most expensive model kit sub-assembly. Before the whole rocket is stacked together, workers build up smaller sections. For instance, the engines aren't just bolted straight to the bottom of the tank. First, they're mounted onto that complex thrust structure we talked about earlier. This creates a complete engine section, or what we call a power pack, with all the engines, turbopumps, and a tangled web of plumbing for fuel lines and hydraulic systems. This is where you really see teams of technicians swarming over the hardware. They are honestly the true artists of the factory floor, armed with massive torque wrenches, wiring diagrams that look like city maps, and an incredible amount of training. They route thousands of feet of wiring through the rocket structure, connecting sensors and computers. They install the plumbing, connecting the fuel tanks to the engines with these thick, insulated pipes designed to carry cryogenic liquids. Every single bolt is tightened to a specific torque value, marked with a special pen, and then inspected by a different person. It's a system of checks and balances designed to catch any potential mistake. In another area, the avionics systems are being installed. The flight computers, batteries, and radios are carefully mounted onto special racks inside the inner stage section or near the top of the rocket. These racks are designed to protect the delicate electronics from the violent vibrations of launch. Technicians then begin the monumental task of connecting everything. It's a spider web of connectors and cables, each one labeled and routed according to a precise plan. They plug the brain into the central nervous system of the rocket, which then connects to the muscles, the engines, and steering systems. This is really where the rocket starts to come alive. At the same time, other teams are working on the payload fairing. This two-part, clamshell-like nose cone is getting prepared for its mission. Inside, they might install the mechanisms that will push the satellite out into space once the fairing separates. They also install insulation and acoustic blankets on the inside walls. These are designed to protect the delicate satellite from the deafening roar of the engines during ascent, which is so powerful it could literally shake a satellite to pieces. Every part of the rocket, from the top to the bottom, is getting this kind of detailed attention, being built up from individual components into complex, functional sections. The puzzle pieces are definitely getting bigger. This is the moment of truth in the factory, the day when all those separate pieces finally come together to form a complete rocket. The process is called integration, or more simply, stacking. It happens in a huge building called a vertical integration facility, which is tall enough to hold the entire rocket standing upright. The first piece to be moved into place is the first stage. A massive overhead crane, capable of lifting hundreds of tons, hooks onto the stage, lifts it carefully off its transporter, and gently lowers it onto the launch mount inside the building. It's a slow, delicate dance with a piece of hardware the size of a small building. Once the first stage is secured, the crane goes back for the next piece, which is usually the interstage. This is the ring that connects the first and second stages. It contains the mechanism that will separate the two stages in flight. The crane lifts it high above the first stage, and technicians guide it down, watching multiple camera feeds to ensure perfect alignment. They might only have a fraction of an inch of clearance. Once it's in place, workers get on platforms and begin the process of bolting the two sections together. These are not just any bolts. They're often explosive bolts, designed to fire in sequence to push the stages apart mid-flight. Next comes the second stage. This is usually smaller than the first stage but is just as complex, with its own engine and fuel tanks. It's the stage that will do the final push to get the payload into orbit. Again, the giant crane lifts it into the air and carefully lowers it onto the interstage. More technicians move in to connect the structural bolts and, just as importantly, the electrical and fluid connections that run between the stages. They are plugging the two stages together so the flight computer can talk to both sets of engines, and so the second stage knows when it's time to separate and ignite its own engine. Finally, the payload already sealed inside its fairing is brought in for the final lift. This is the most precious cargo of all, often a satellite worth hundreds of millions of dollars. It's hoisted to the very top of the rocket and gently lowered into place. With the final set of bolts tightened, the rocket, for the first time, is fully assembled. It stands there in the high bay, a towering, gleaming testament to the thousands of hours of work that went into its creation. It's no longer a collection of parts, it's a vehicle, poised and ready for the next and most critical phase of its life: testing. Just because the rocket is built doesn't mean it's ready to fly, far from it. Now begins the most critical phase of all testing. Every single system, from the biggest engine to the smallest switch, must be proven to work perfectly. One of the first major tests is a tanking test. The rocket is filled with its cryogenic propellants, super-chilled liquid oxygen and liquid hydrogen or kerosene, to see how the structure and plumbing handle the extreme cold and the weight. Sensors all over the rocket measure temperatures and strain to make sure the tanks don't crack or leak as they shrink in the cold. It's a dress rehearsal for fueling on the launch pad. Then comes the test that everyone loves: the static fire. This is where the rocket is held down with massive clamps and its engines are fired up for a short duration, sometimes for the full length of a mission burn. It's an incredible spectacle of controlled violence. The ground shakes, a deafening roar fills the air, and huge clouds of steam billow out from the flame trench. But for the engineers, it's all about the data. Thousands of sensors are recording engine pressures, temperatures, vibrations, and thrust. They are checking to see if the engines throttle correctly, if the turbo pumps spin up smoothly, and if the whole system works together as designed. A successful static fire is a huge milestone. It's not just the big systems that get tested. Every individual component has already been through hell and back before it was even installed on the rocket. Electronic boxes are put on shake tables, powerful machines that vibrate them violently to simulate the bone-rattling forces of launch. They're also placed in thermal vacuum chambers, which suck out all the air and cycle between extreme heat and cold to mimic the environment of space. Engineers test valves by opening and closing them thousands of times. They test separation systems by actually firing the explosive bolts to make sure they work on command. It's a philosophy of test, like you fly. This culture of testing is all about finding problems on the ground where you can fix them. A failure in a test stand is a lesson learned. A failure in flight is a disaster. Technicians will run full wet dress rehearsals where they go through the entire launch countdown, fueling the rocket and proceeding right up to the moment of ignition, then stopping. They test the software, running millions of simulations of the flight path with different potential failures to see if the computer can handle it. The goal is to build confidence, to prove to themselves and to the mission managers that this vehicle is as safe and reliable as humanly possible. Only then can it be cleared for its journey to the launch pad. After passing every test, simulation, and inspection, the rocket is finally deemed flight-ready, but the work isn't over yet. The rocket must now be transported from the assembly building to the launch pad, which can be several miles away. This is another incredibly delicate operation. The rocket is carefully lowered onto a massive transporter vehicle. These transporters are amazing machines in their own right, designed to move at a snail's pace, maybe 1 or 2 miles per hour, and keep the rocket perfectly level, even as they go up and down ramps. It's a slow, majestic parade, the rocket's first journey into the outside world. Once at the launch pad, the whole process of lifting and securing the rocket is repeated. It's raised to a vertical position and attached to the launch tower. This tower is more than just a support structure. It's the rocket's umbilical cord. It provides power, data connections, and most importantly, the propellants that will be pumped into the rocket during the final countdown. Teams of technicians swarm the pad, connecting thick hoses and electrical cables between the tower and the rocket. This is the final hookup, preparing the vehicle for its last moments on Earth. It's a race against the clock, often performed in the dead of night under bright floodlights. The final checks are now conducted remotely from the Launch Control Center, a bunker-like building located a safe distance away. Engineers at their consoles perform a final series of health checks on every system. They verify that all the connections are good, and that every sensor is reporting correctly. The weather officers give their final forecast, looking for any sign of high winds or lightning that could scrub the launch. The range safety officer confirms that the ocean downrange is clear of any ships or planes. It's a complex, highly choreographed sequence of go or no-go polls, where every team leader has to give their final go for launch. In the final minutes of the countdown, the rocket takes over. The ground computers hand off control to the rocket's own flight computer. The umbilical arms on the tower swing away. The sound suppression system begins to flood the pad with hundreds of thousands of gallons of water to absorb the acoustic energy of the engines. And then, at T0, the commands are sent to ignite the engines. For a few heart-stopping seconds, the rocket's computers check that all engines are running at full power before commanding the hold-down clamps to release. Only then, when everything is perfect, does the giant machine finally begin its climb to the sky, leaving the factory and its builders behind. So why go through all this trouble? Why the clean rooms, the endless testing, and the almost obsessive attention to every single bolt and wire? The answer is simple. The stakes are astronomically high. When you launch a rocket, there are no second chances. You can't pull over to the side of the road if something goes wrong. Every component has to work perfectly the first time in one of the most hostile environments imaginable. The forces of launch are trying to shake the rocket apart, the temperatures are trying to melt it, and the vacuum of space is waiting to challenge it. Building with care isn't just a good idea, it's the only way to succeed. Think about the cargo. Sometimes it's a multi-billion-dollar science telescope, the product of decades of work by thousands of scientists that will help us see back to the dawn of time. A single loose wire or a faulty valve could turn that dream into a cloud of smoke. Other times the cargo is even more precious: human beings. When astronauts strap themselves into the capsule at the top of that controlled explosion, they are placing their lives in the hands of every single person who designed, built, and tested that vehicle. That is a sacred trust, and it's the reason for the relentless focus on safety and quality. This meticulous process of building rockets does more than just get us to space. It pushes the boundaries of what's possible in manufacturing and engineering right here on Earth. The techniques invented for rocketry, like friction stir welding and advanced composite fabrication, find their way into other industries, making our cars safer, our airplanes more efficient, and our medical devices more reliable. The pursuit of perfection required for space travel raises the bar for everyone. The factory is not just building rockets, it's building the future of technology. It's a laboratory where we solve the hardest problems and the solutions benefit us all. Ultimately, building rockets carefully is our commitment to the dream of exploration. It's about honoring the human desire to see what's over the next hill, or in this case, the next planet. Each rocket that successfully roars to life from the launch pad is a victory for curiosity, for ingenuity, and for collaboration. It represents the very best of what we can achieve when we work together with precision and purpose. The factory floor is where that journey begins. It's where we turn metal, fire, and ambition into a machine that can carry our hopes and dreams into the final frontier. And that is a job worth doing with the utmost care.